small for this big room, isn't it? That's there. So, room selections are somewhat interesting here because I teach a class on microprocessors that I'm squeezed into a lab upstairs when I've got both sections together that should be in this big room because they have to go out and get chairs in the hallway. There's like 35 students and like 25 seats. And then I've got this smaller group here in this great big room, so that there. But I don't assign that there. So let me kind of go through here. This is the chapter 4 slides out of the Tochi book. Now, as I recall, earlier in the semester I gave everyone copies of Tochi and Floyd. So I'm going back to the Tochi book. The last couple of slides I used Floyd. The material is really the same type of material, but they approach it differently. We've got enough time to kind of go through both approaches to make sure that and the reason I go through both approaches is because it is material that is somewhat, So again, this particular chapter covers a few things better, but this is a complete review, and I'm going to go through it relatively quickly right there. We're going to spend a little bit more time on hierarchical design methods, and then once I'm done, I'm going to move into the next chapter where we're going to get into an example. So I'm not going to spend the entire class today going through these slides. I'm going to move on to the next set there. So, and then I'm going to spend a little bit of time talking about HDL. I wasn't going to, but I think it's kind of easier to just kind of carry that along as we go through that there. And it's not really part of the curriculum right now for this course, but it's going to be added to the curriculum, HDL, and it's going to be at there. So there won't be anything on the final exam on HDL, but my philosophy going back is not how well you do on the final exam, it's how well you know this material and when you have to use it in industry. That's it. So, okay, we've talked a little bit about this before, but again, this kind of goes into it in a little bit more detail and a little bit more specifically. A sum of products actually consists of terms. Here's a term, that are added together right there. So a sum of products will appear as two or more and terms that are ORed together. And this is a very important concept because it allows us to easily develop PLDs right there, because this is simply going to be an AND gate, an AND gate, an AND gate, all ORed together right there. So we have this type of structure there. Now, something to keep in mind, and I'll remind you as the final exam comes, when I ask you to draw circuits on final exam, you do not have to show an input and then a wire here. You can actually just show A going here like that there to simplify your drawings. That's there. And the software that I use actually allows you to do that there. The Cordis allows you to that there. So again, this is the sum of products that are ORed together right there. And then the other term we have is a product of sums. So those are the two ways that we typically write Boolean expressions in standard form. A product of sums or a sum of products. That's there. Now, what that essentially means is that when we look at a sum of products means that the circuit is going to look like this right here. Right here. Right here. Like this. And we have all of our inputs coming in here, like this. We won't worry right there. And when we have a product of sums, or a sum of products like this here, that if I draw this as a NAND gate, and this here, we have not changed this. This, as it turns out, is also a NAND gate. So a product, or a sum of products, is always going to result in a NAND gate configuration. Right there. That's why it's important to look at the sum of, as we look at a sum of products, we do it like that. If we have something that looks like this, which is A plus B naught plus C A naught plus B plus C, A plus B plus C. This is a product of sums, right there. So we have 3 OR gates right here going into an AND gate right there. And again, if we do our bubble trick here, this is going to end up with a NOR configuration right there. So we have 2 ways that we can write our standard circuits. What we've been using for the most part is a sum of products. That's what most people tend to use as students. Out in industry, they tend to use both. Right there. So most of the examples in the book are going to be the sum of products. That's there. Now, one of the reasons the sum of products is so common is if I go through a truth table, A, B, C, right here, here's X. Right here. And I'm just going to do a couple. Right there, 3 there, that I can instantly write an expression for this table by just simply saying that it's going to be A naught, B naught, C naught, or A, B naught, C naught, or A, B, C equals X. In other words, I can pull that straight right off the table by looking at there. So it's very easy to work with the sum of products right there. That's there. So that's why people tend to look at it that way there. So a sum of products will give us this type of expression there. Now, if we want to use NOR gates, it's more difficult. That's there. And the reason NOR gates are more difficult is because we have to use Karnaugh maps twice. And I don't think I've gone through that process with this group here yet. That's there. So, but I will go through it in a little bit here with another example. Let's say, well, let me just go ahead and do it right now. Let me just kind of go through here. And let's say I have a circuit that looks like this. X. We're passing attendance sheets around, huh? Is that there? I already marked everybody here. I take attendance, to be honest, at kind of random variables. Okay, right here. So this is our right here, and I'm just going to 1 1 0 1 0 1 1 0. Okay, that this particular case that there. If I'm going to use NOR gates, that means I want my in a product of sums, right? The product of sums. I want it in this configuration, right there. And the book may not do a very good job of explaining this. What I have to do is I have to read out the zeros. And that's kind of confusing, this process. That's why I'm taking a little bit of time going through this. And I don't think the book covers it very well, if they do it at all. Right there, some books tend to that there. But if I read out the zeros, right there, here's a 0. Excuse me. I meant to put the mark here, 0, 0. In this particular case, I have 3 zeros right there. So if I read out there, that is the function x naught is equal to. That's what the function is not right there. Is equal to A naught B C naught, or A B naught C naught, or A B C. So anything else, the function is going to be a 1 right there. So this is what the function is not. I'm reading the zeros out. That there. So as we go through here, and we say that, let me lasso this so that I don't have to redraw it, right here. I have to copy right there. So if I write that as a function, I can say the function x is equal to a naught b c naught plus a b naught c naught plus a b c, all with a naught on that there. I inverted both sides, is what I've done that there. So this is what the function is. Now I have to use De Morgan's rule right there. And De Morgan's rule is going to be then, the function is a naught b c naught, all with an and over it, a b naught c naught, all with an and over it, a b c, all with an and over it. That is what my function is. So now I apply De Morgan's rule once again. So our function is a plus b naught plus c naught, or plus c, a naught plus b plus c, a naught plus b naught plus c naught, right there. Now it's in a product of sums where I can use NOR gates right there. Right there. So it's a little bit of a process to go through. And I didn't cover this back when I originally talked about reading things off that there, because it's different. But you have two ways of developing your equation. Now, this is not the simplest form. We're going to go through the same thing here in a minute using Karnoff maps. Right there. That there. So, that there. This is just going from the truth table. We're writing our expression without simplifying it, and we're inverting. We're reading the zeros out. We're saying the function is not this. So the function is that all inverted right there. So we're saying the function is not something here, right there. So we can turn right around and say the function is this with the not sign on it right there is what we're doing. So that is the trick we're pulling in order to read this table out in NOR gate configuration right there. So now our function is going to be 3 NOR gates right there. I'm drawing it as ORs right now with A, B naught, C, A naught, B, C, A naught, B naught, C naught. Right here, we then do this, and this is now a NOR gate configuration right there. Now, how will we do this with Karnoff maps? The same way. We read the zeros out. That there. We do the same thing. We read the zeros out. So again, I'm going to just kind of put a random one here, and I'm just going to do this up to 3. We could do it with 4. It doesn't really matter. Well, let's just say that A, B, C. Here's X. All right, and 0, 1, 1, 0, 1, 0, 0, 1. Okay. Now, a normal Karnoff map, let's just go ahead and fill the Karnoff map. A naught, B naught, A naught, B, A, B, A, B naught, C naught, C. So, 0, 1, 1, 0. And 0, 1, 2, 3, 4, 5, 6, 7. So 6 is going to be 0, 7 is a 1, 4 is a 1, and 5 is a 0. And I have managed to do the absolute worst Karnaugh map. The reason is there's absolutely no pairs whatsoever. How I managed to do that, I don't know. But I managed to put this Karnaugh map. Does everyone see that there's absolutely no pairs in either the 1s or the 0s? Right there. So, with that said, we're going to change it. You know, if the example's bad, let's change the example. Right here. I'm just going to fill in the Karnaugh map 1, 1, 0, 0, 1, 0, 0, 1 right there. That doesn't match this right here with 1, 1, 0, 1, 6 is a 1, 7 is a 0, 4 is a 1, 5 is a 0. Okay. So I changed the example just because, so that the example makes some sense right here. At this point, I can read out the 0s, or I can read out the 1s. This is where you make the decision whether you want to do NAND gates or NOR gates. If you're going to do NAND gates, you read the 1s. If you want to do a NOR gates configuration, we read out the 0s. This is a sum of products. This is a product of sums right there. So we're going to read out, in this particular case, our previous one will read out the 1s. I'm going to highlight, circle this so that I can copy that, so that I can do it again right here. So let's start off here, and let's just read out the 1s here. So if we read out the 1s, our circuit is, we have a pair of 1s here and a pair of 1s here. We have two terms in this particular one right there. We don't need to read this one here because both the 1s are taken care of. So this pair here is going to be, it looks like B naught, C naught. And this pair over here is A naught C right there, is equal to X right there. So that's our simplest configuration using NAND gates right there. Because then we would then draw that circuit B naught, C naught, A naught, C, and right there, and then this becomes our NAND gates right there. So that's one way of coming up with that there. Now, if you're using discrete logic or coordinates or programmable logic, a lot of this discussion doesn't matter. This is only if you're going into a gateway. If we want to do the same thing right here, but this time we want to use NOR gates, so we want this to be a product of sums. We read out the 0s right there. So as we read out the 0s in this case, we read out one pair of 0 and another pair of 0s right there. So our circuit doesn't get any simpler right there. This is B C naught, or, and this A naught disappeared there, that naught disappears. So that's B, excuse me, no, my brain is, that's it there. This is AC right there, okay. Right there, that's AC, right there. So this is what our function is not, right? Because I read out the 0s. So our function is going to be B C naught AC, B naught plus C, A naught plus C naught, right there, is equal to X, right there. Now, if you do this a lot, you can skip these steps right here. But I don't recommend that you do that. I recommend that you go through these steps, because you're probably only going to do this once or twice more before the final exam. So if it's on the final exam, you're not going to be experienced enough to see these two and then write out. Looking at these two, I see that that's B, C naught, so I would write B naught plus C right there. I would invert those automatically. I don't recommend you do that. I recommend what you do is that you say, this is what the function is not, you read out the zeros, and then you apply De Morgan's twice in order to get the right answer right there. So, all right. I kind of went off the reservation a little bit with that discussion right there. But as I recall going through this, they don't really go through it in that much detail. So I'm just going to, all right, we've gone through this, examples like this before. This example here, this is a good example. I will make sure if I haven't posted them, I will post. Oh, is this the class where I did not tell you about the Facebook page, right? Okay. I should point out that I put pretty much all the lectures and everything are put on a Facebook group page, or a Facebook group for this class. So if you have not asked me to be added to that group, you need to do that right there. And if I can find it here, if I have Facebook, I'm on this computer right now. That's I had. Yep, I don't know. Yeah, this is the right one. But there's a group here called Digital Electronics. There's actually two of them. The one that you want is the one that says September 2015. You want to be added to that group right there. And then you'll see things like lectures for September 17th lecture there. I should have had one for the other day. What? September 18th? This is not this. Oh, no, this is. Yeah, September. Yeah, I didn't put. No. I should have had the. Yeah. Oh, here's the lecture for 29 September right there. That's the one from 2 days ago, right there. If you go through here, you'll find the lectures for 10th, 15th. So anytime I record a lecture, I post it on that there. So, and most people are pretty good at. Yeah, that's there. And who is this here? Yeah, it's easier to just right there. I don't use this Facebook page for anything personal, so it's right there. So I got a few people that have added me to it, so you might see some stuff on the personal nature, but I don't normally. If you go through this group, it's only on this class. This is a public group, so if you don't get added to the group, you can still see the page. I don't hide the page. There. So I just wanted to point out that it is there. There. I have two Facebook pages. One shows this picture here. That's the one you want right there. What else? There's a picture of there it is. My wife and I at the Grand Canyon. There. And you can see my wife is freezing to death in the Grand Canyon. It was about 4 or 5 degrees when we were there that day. 2 days later, it snowed like crazy, so we were there in December. There. Okay. All right. The reason I mentioned the Facebook page is that's where these lectures show up, and if you want to review the lectures, that's where the links are. The lectures themselves are actually on YouTube. There. I tried putting them up on the e-learning site that UniKL has, and I discovered that it's only good for like 15 minutes of a lecture at all. That's the most you can record. And for me to break my lectures up every 15 minutes, stop and start a new recording, and then spend the time encoding 5 different lectures for an hour, 15-minute lecture, it's a pain in the neck. Easier just to do one 75-minute lectures, which is what mine at there. Okay, getting back to from current slide, there. This particular circuit right here, we've done ones like that. Again, you see this This is BC, and okay. And don't tell me my pen is not wanting to work. I had my Bluetooth completely disconnect on me. Okay, this is BC, that's the output from here. This one here is ABC, not right there. This is the simplification, but again, what we're showing here right there, is that this is what the circuit is, and through simplification, they determined that there. I'm not going to go through the process. We went through that enough. That's going through there, and this is going through the steps. I'll place these slides up there. Get that there. This is actually a pretty good example right there. Simplified circuit. Right there. Okay, to solve any logic problem right there, this is basically, they're saying that the best way to start things is to start with a truth table right there. Again, my feeling is that we come up with a truth table there, and what they're showing here is that they're going from the truth table and just implementing the circuit directly here in sum of products notation right there is what that is, all this particular slide is saying. We've gone through that half dozen times right there, and again, they're showing you just how to read the truth table right there. So again, we've got simplify, and this looks like pure garbage here. I don't know, there's something right there. Oh, this is a typical problem here where they're saying design a logic circuit with 3 inputs. The output is to be high only when a majority of the inputs are high, right there. Now, what they're not showing you is this simplified expression is messed up there. What it should be, if you look at this right here, is and I'm going to write it on here, A, B, C. I'm going to have to write it small right here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And what they're saying is, when the majority of the inputs are high, the output should be high. And this particular example, they don't give you a truth table, but you can say if there's 2 1s, the output or more, the output should be high. So this is 0, 0, 0, 1, 0, 1, 1, 1. So that is what your truth table should look like right there. So what they should have done here next is simplified expression. This should have been A not B. Got a 1 here, a 1 here. A, B, that there, another 1 here, right here. And I don't know what these are right there. So, but that's a simplified expression right here, or before you do the simplification, and you can go through and manipulate that to come up with this right here. I personally don't do a lot of Boolean up there. The Karnoff map, I'm not going to go through that again up there. This does a very good job, these sets of slides, and I'll post these slides actually on Facebook as soon as I'm done with today's lecture, so that you can follow these slides, because these slides are probably as good an example as what I've done in class, step by step right there. So, and I can guarantee you that on the final exam there will be at least one Karnoff map problem right there. So this goes through all the various groupings you could possibly come up with right there. Right there, this gives all the explanations group right there. Now, one of the things that you should keep in mind is that this does a very good job of doing the Karnoff map for the sum of products It doesn't necessarily cover the product of sums method. The product of sum methods, you know, where we're going into the NOR gate, the one I just talked about, where we read out what the function is not, you have to add to this discussion how you would do that right there. So this does not do a good example. There's enough information between what I gave you there and how the kernel maps to do that. But if you go back and look at, yeah, let's just go through it. Right here, you would read out the zeros instead of here. In this particular case, if you're going to do this in a NOR gate configuration, I would read out the zeros and accidentally right there. So I've got a group of 8 right there. I've got a group of 4 here and a group of 4 here. So that's how I would solve this problem right there. So my group of 8 reduces down to 2 variables, and it looks like it's going to be actually a group of 8 will reduce down to 1 variable, and that's going to be D naught, right? This is what the function is not, is D naught. This group of 4 is going to be A naught C, A naught C, that's that group of 4 right there. And then this group of 4 down at the bottom is going to be A B naught right there. So that's what the function is not. And then you apply well, let me, right there. I don't have an easy way of copying that there. So this is what the function is not. So D naught plus A right there. So you would then say that the function is D naught or A naught C or A B naught, all knotted. So the function is D naught naught right there times A naught C knotted times A B naught, all knotted right there. So then you would simplify that again. That would be D ended with A plus C naught ended with A naught plus B naught, or excuse me, B right there. And this is what the function is not right there, or what the function is, excuse me, right there. That's what the function is. So again, that's the process you would apply right there. So you're looking at this example, I read out the zeros and then I apply De Morgan's rule on it right here. I applied De Morgan's rule on it twice to get this right here, and then this is one application, and then this is the second application, and that gives me what the function is right there. So these slides show you very well how to handle the sum of products. They don't necessarily show you how to handle the product of sums, but what I showed you earlier on reading out the zeros gets us to the same place right there. So, okay, out there, and this is actually a fairly good right there discussion right there. I will have to give. I bet you Neil did these slides. This doesn't look like Greg's work. Right there. The exclusive OR I kind of flew over. I'm not going to worry too much about the exclusive OR. You do need to know what it is. I talked about it before. Right there. There's also the exclusive NOR. Right there. Which is the opposite right there. Those are used a lot in comparators and parity checkers right there. And they're also used in adders in some cases right there. So this is a case where they're using the exclusive NOR to look at two binary numbers and comparing them to each other right there. What we're saying when we look at this right here, first off, let's go back and look at the truth table for the NOR. Notice that the output of an exclusive NOR is high if both inputs are the same. It's low if the two inputs are different. So if I want to compare two numbers together right here, what this is basically going to say is that if x1 is equal to y1 and y0 is equal to x0, both these are going to be 1, and the output is going to be 1. Any other combination is going to give me 0, is what that does. All this is saying is x1, x0 equal to y1, y0 right there. We're comparing two binary numbers together. And if I want to compare it to 8-bit numbers, I just stick 8 XNORs in there. Because for two numbers to be equal to each other, all the bits have to be exactly the same. So I can just add more of these, and add more inputs on this right here. So it's very easy to use XNORs for doing comparators right there. And again, how an XNOR circuit, they're showing, I don't want to spend a lot of time on XNORs, and I think they actually go through a little bit more time on XNORs there than because 90% of logic today is implemented into some form of programmable logic. And programmable logic takes on multiple forms. We haven't talked about it in great detail. One we talked about is the programmable logic array, where we have a bunch of OR gates that feed into a, or AND gates that feed into a OR gate. We will often use lookup tables there, or we will use field programmable gate arrays, which is nothing but NAND gates or NOR gates. So the XOR isn't used very much at all in terms of today's programmable logic. And the reason is that it may reduce the number of gates, but if you've got 2 million NOR gates on an IC, what difference does it make? As soon as you start putting a different type of gate into the circuit, you've complicated things. So it's easier to implement something with a gate array with nothing but one type of gate on it than to play around with multiple types of gates right there. So that's why the XOR and the XNOR have some very useful properties when we look at understanding some circuits, but implementation, you just don't see them that much anymore. But parity checkers are important for what they are. How they're implemented is not that important right there. What a parity checker does is it checks, and you can generate the parity or you can test for parity. And what a parity checker does is it looks for even or odd numbers of ones in that there. And if you generate parity, that there, you're either going to generate a 1 or 0 in order to force the number to be odd or even ones that there. So for example, I want even parity. And let's look in at a even right there, D. I'm surprised I don't dream in ones and zeros by the time I get done teaching this class twice in the same day. I'm going to stop there because for sake of even, P odd, right there. All right, what we're looking for is P even, and this is odd here, is that we're going to generate a bit in order to, when I transmit this data, for checking for errors. Has anybody ever used a computer system where it says parity check error? You've never seen that error before. That's it. Okay, well, a lot of they use other systems a lot of times now, but they're still used for, you know, for some systems up there. A parity check is a way of testing for bad memory, for example. Right there. You know, the early computers, memory was individual chips, and sometimes a chip would go bad, and you would end up with a parity check error when you boot it up. The early IBM PCs, you actually had one chip for every bit of memory that's there. So you could actually look at the check error, and you could tell which memory chip was bad. So, you know, the early IBM PCs would have one row of that there, and there'd be 9 chips right here, right there. 1, 2, 3, 4. So there'd be 8 data chips and a parity bit check. And then there'd be another row and another row right there. Now, of course, they put all the rows on one chip, so it doesn't matter. You have to throw away the whole module. That there, you used to be able to replace the individual chips on the modules. So, but they were a lot bigger. So nowadays, when you look at a memory module, it's got probably between 8 to 16 chips on the module, and the module plugs into the motherboard. And I think everyone's seen how memory's added to motherboards. That's there. Well, the early days, there weren't these modules. The chips themselves went onto the motherboard. And you would buy the individual memory chips, which meant if you wanted to expand memory, you would have to buy 8 or 9 chips. That there. And you would put them in individually, one at a time, into the socket. That there. So, what you would do is they would set this up for even or odd parity, and the parity bit is excess. It's not part of your data. It's just excess information, only used for checking for errors. Right there. And what we do is we set the parity bit to either even or odd, and you can do it for either way. It doesn't make any difference. A lot of serial communications, if you're looking at serial communications from computer to computer, a lot of the early modems use serial communications, and you would do parities that there. If you talk processor to processor, you would set up whether you would have even parity, odd parity, or no parity. Right there. So if we had even parity, that there means that if our number of bits are 0, our parity bit's 0. If our number of bits are 1, our parity is 1. If it's 2, it's 0. If it's 3, it's going to be 1. 4, it's going to be 0. You can see it's, you know, if this number is odd, we're going to place the parity bit to be a 1 so that we have an even number of 1s. If the number is already even, we don't want the parity bit to be a 1 because you already have even parity. So this would be 0, 1, 0, excuse me. This would be a 1, a 1. This would be 0. This would be a 1. This would be 0. This would be a 0. This would be a 1. A 1, a 0, a 0, a 1, a 0. You can see the pattern there. I'm not looking at the number itself, whether it's even or odd. I'm looking at the number of 1s there are. Here there's 2 1s on the second one. The first one I circled, it's got 1 1. This has got 1 1, so I set the parity bit to be a 1, so now I have 2 1s in the number when I read it. Not the number of 2, but there's 2 1s in that there. That's what we're looking for right there. And odd is just simply the reverse. Right there. We don't even have to calculate the odd, it's just going to be the reverse. Right there. Right there. So that's what parity is. And it goes, the parity bit just goes along for the ride in order to help us at there. I'm going to transmit 8 bits over a serial cable right there. We haven't talked about serial parallel communications. At the end of the transmission, I want to know whether I've got the right data. That's there. Now, parity is based on statistical analysis, which we're not going to go through. This is not a course on statistics. But statistically, the odds of 2 bits being wrong in the same byte is very, very small. The odds of 1 byte being wrong is relatively significant, but having 2 errors in the same byte is relatively small, right there. So in that case, we catch about 99% of all errors by using just simple parity checking, right there. So parity checking has been around ever since the days of digital communications. It's still the most common way of doing a memory check. When you go through your system, when you first power it up, it goes through and checks all the memory. It's actually using a parity check process where it's going through. Now, they've actually gotten a little bit more elaborate, where they write a series of 1s and 0s and test them that there, because the computers are much faster at doing memory checking. Remember that the original IBM PC, well, you don't remember, you weren't around, but it operated at 4.77 megahertz. Today's computers are operating in the 1.5, 3.0 gigahertz range. That's a multiplier of megahertz to gigahertz is 1,000 times faster, roughly. So going through and checking memory is much faster today. But the memory that it checks is much more today. My first IBM PC came with 64K of RAM. We're not talking 64 meg, we're not talking 64 gig, we're talking 64K. 64K is 64,000 memory locations. That sounds like a big number, but it's not. My current system that I run for doing recording and encoding videos at home, where I do more video editing, I've got 32 gig of RAM. So a jump from K to meg is a jump by 1,000. A jump from meg to a gig is another 1,000. So that's 1,000,000 times more memory, or 500,000 times as much memory. So you can see the exponential growth in memory out there. Some of you have got cell phones that have got 3 gig of RAM in it, I would assume, right? Most cell phones have between 1 to 3 gig of RAM. If you've got something like a Galaxy Note 3 or above, it's going to have 3 gig of RAM. If you got something like the A5 or some of the smaller Samsungs, are going to have probably 2 gig or a gig and a half. I think most of the Apples only have 1 gig to 2 gig of RAM. Apples actually have less memory than the Samsungs. That's there. So that's there. But that's parity. So as we get away from parity, this whole discussion on parity, this is the circuit required to generate the parity. As I said, I don't care so much about the circuit. I'm more concerned that you understand what parity is meant, what is meant by parity, right there. See, and again, this generates the parity, and all this does is it looks at the 4 bits coming in, and then it generates a 5th bit that's going to be even or odd, or even in this case. If I want odd parity, all I have to do is put a bubble there, right there. And even parity is the same thing, right there. I have 5 bits coming into it, and I check to see whether or not it's even or odd. And the exclusive OR is brought up here as a way of justifying what the exclusive OR is used for. Got there. So we haven't talked much about this particular subject. I want to just kind of go through. We will see certain circuits that will have enable or chip inputs. This is showing here, for example, that I'm using B as an enable in order for this to go through, right there. If B is equal to 0, this signal does not pass. Is all that this is saying right there. Right there. Is all we're using is we use an AND gate there as an enable pin right there. We can use an OR gate, and if the OR gate means that if B is 1, the output is simply going to go high and stay high. If we're using a NOR gate, if B is 1, the output is going to go low and stay low right there. So all we can use an OR gate, an AND gate, an NAND gate, any of the 4 gates, basic gates there. When we say basic gates, I'm talking AND, OR, NAND, and NOR. The NOT gate and the inverter, those are used for other things out there. We don't use them out there. So they can be used for enabling and disabling signals right there. So again, an enables logic that allows a signal to pass through only when the controls are both high. This has got 2 enable lines right there. So this is here again, having another circuit here where we're out there. I'm not too concerned with you knowing these circuits out there. In other words, don't spend time memorizing these circuits right there. So this is big, again, we've got here logic circuit with an input A, controls B and X which operates. This is basically coming through here, and this is saying that the signal goes, A is going to go, if B is high, the signal is going to come out here. If B is low, the signal is going to come out there. So this is very commonly used for multiplexing circuits. In other words, I have a signal that comes in, it can either go here or it can go here. And we'll talk about multiplexers there. So we decide which way they're. These circuits are used a lot in, say, for example, telephone switches. Because what we're relying on the fact is that we've got one signal that is a pulse train, not a 1 or a 0, but the pulse train. And we want to send it to either this location or this location, right there. And we use this type of circuit for routing. And we'll see multiplexers later, but this is kind of the basics of how multiplexers work right there. Okay, as I said, I'm just going through these slides right there. They talk about complexity. You're going to hear these complexities up there. This is a moving slide. It changes every year. It's already out to date. And the reason is this is saying gigascale integration is 1 million gates or more on a single chip. That's not considered an extremely large chip by today's standards, right there. The slide was written, it says copyright 2011, so this particular slide is at least 4 years old or 5 years old. It may be much older than that. Right there. So the concept is the same. Small scale integration, those are SSI chips. Those are those small chips that this book talks about out there where you got 4 AND gates on a chip, 4 NOR gates on a chip, 6 inverters on a chip. You got fewer than 12 gates on a chip. That's it. Medium scale, you're getting into things such as adders, multipliers, multiplexers. They're 12 to 100 gates per chip right there. Large scale, you're getting into probably some programmable logic, maybe some very small ALUs, multipliers right there. VLSI, you're starting to get into some real chips. You're starting to get into microcontrollers, you're starting to get into ASICs, that's there. Now, this says up to 100,000 gates. 100,000 gates is nothing anymore. We look at the chip that I brought in on that little board I brought in the other day in class. It's got 484 I/O pins on it. That's there. So, and it's got probably 500,000 gates, something like that on it. And that's not considered a very large chip. Something like an i5 has got close to 1 billion transistors. That's with a B. So, but the concept is that we get into the manufacturing process. I'm not going to get into. This is what this book typically talks about is traditional TTL logic, where we teach digital electronics uses SSI chips and they're 14-pin chips. We're not going to see any of those, so I'm going to kind of go through. This is the common numbering system. It goes around like this right here. Pin 1 to pin 14. 7 to 14 are VCC and ground typically, right there. So internally, this is kind of an interesting slide, and I want to point this out. When they make a chip, it's a round piece of silicon wafer. And they actually make the chip, it's a wafer, and when I was a kid, and I don't think it's done much in schools anymore, we used to do something called make rock candy. And that is you put a string or a thread into a glass of water, then you heat it up and you fill it with sugar. So that the sugar there, and then the sugar will form a very large crystal on the string, right there. And you can do it with salt as well. But you could form crystals onto a string. And we would call it rock candy because all it was a giant sugar crystal. And you'd sit there and lick it. Parents hated it because the kids would be hyper for days after eating a big piece of rock candy. That's there. I haven't seen it in a long time because I think the dentists of the world united and banned using rock candy labs in elementary schools. So you probably haven't seen it because I haven't seen it done in the U.S. But that's how a crystal is formed. Right there. And they do that with silicon. Silicon is basically a compound, and sand is about 90% silicon right there. So there's lots of silicon. We're not going to run out of sand. There's enough sand in the deserts of Arizona, New Mexico that keep the U.S. going for 1,000 years, and then we could always go to Saudi Arabia, and there's lots of sand there, right? So sand is not a scarce commodity. So we're not going to run out of silicon right there. So we form these silicon wafers, and a silicon wafer is pure silicon right there. Now silicon as itself is a material that doesn't conduct well and it doesn't insulate well. Since they call it a semiconductor, it semi-conducts right there. And it goes through a manufacturing process there where we take our piece of silicon right here, and it's a round wafer, and we cut it. It's cut into slices. You'll hear it right there, and it's cut into slices right there, right there. It's not a wafer. It's a big cylindrical tube, is what it is, right there. And it's cut into thin slices, right there. And each one of these is referred to as a silicon slice, right there. And then it's placed, and we're looking at from the top there. It's placed in a container, and they put a mask over it. They put a mask here, a mask here, a mask here, a mask here, a mask there, and then they expose it to some type of gas right there. That changes the molecular structure of the silicon. It adds impurities to it. Now, silicon has got 4 electrons in the conduction band. Now, that if you don't remember your chemistry, that probably doesn't mean much to you, but the ideal material that all compounds strive to get 8 electrons in the conduction band. That's the ideal that there. The exception is helium, which has got 2. All the natural elements that have got exactly 8 or 2 electrons in the conduction band, that there. Helium's the exception. Everything else is, there you go. It's called an inert gas. It will not mix with anything. It will not form compounds. You cannot have helium sulfide. Helium does not bond with anything. Water, for example, has got H2O. There's 2 electrons or 1 electron in the hydrogen band, 6 in the oxygen band. So hydrogen shares one of its electrons with the oxygen, and it takes 2 hydrogen atoms to form H2O right there. And what you have with H2O is here's oxygen that's got 6, and I'm going to show 1, 2, 3, 4, 6 here, and then here's helium over here, that's got 1 right here, right there, and here's another helium that's got 1. And this 1 goes around through, and then one of the oxygens is shared. So this forms H2O. And actually H2O is actually at 120 degrees is the way it forms. But these things, this is how chemistry works right there. Well, silica, because it has 4, will form a very nice crystal with 4. It forms a perfect crystal with 4 because it shares with 4 others. Here's 4, it shares with these 2, it shares with these 2, it shares with these 2, it shares with these 2. So it's sharing right there. Well, we add something to the mix. We add arsenic, we add boron, we add something. Some of the crystals will now have impurities, and there'll be only 5 right there. In other words, we have an extra proton or electron floating around there. That's a negatively charged piece of material. Or we have a hole missing. We only give it 3 electrons there instead of 4. So when we do that, we have positively charged pieces of material right there. And that allows us to make things such as diode, transistors, and everything like that. And this is actually should be part of your first course in semiconductors right there. So you should have heard this material before. But as I'm looking around the room, I see a lot of people saying, yeah, all right, I don't remember this. Right there. But the process of making a IC means that we add impurities to that have either 3 or 5 electrons in the conduction band. That's there. If we have 3 electrons in the conduction band, it's positively charged because it's missing a negative charge. An electron has a negative charge right there. So if it's got 5, it's positively charged. So we form what they call N material or P material. And if you look at something like a diode right here typically has some P material and N material, and then we have what's called the little junction right there, and we can positively charge we can forward bias or reverse bias the diode. Transistors typically have 3 regions, PNP right there, or PNP right there. So that's how we form our IC, is that we continuously put mask on, we expose it to something. We put another mask on, we expose it to another compound, we put another mask. So we form transistors on this crystal right there. So we form transistors on this crystal, and we actually fabricate the crystal. I personally have never worked in that industry. So I've been to IC plants. I've had friends of mine that worked in that industry that actually did the fabrication right there. If you look around, there's a number of fabs in Malaysia. They actually do a lot of that work in Malaysia. A lot of it's done in the Philippines. A lot of it's done in Singapore. Has a number of fabs. Some of it's done in Thailand. A lot of that's done in Southeast Asia. It used to be done in the U.S. Very little of it's done in the U.S. anymore. Right there. So, but regardless, right there. So they form this crystal, and then they cut it into little pieces. Each one of these pieces is called a die, right there. Right there. And that has one circuit, right there. And then, of course, they go through and they test the circuit and make sure it's good, and they throw out the ones that have impurities. This is a process that has to be done in a very clean environment. Right there. If you've ever been in a IC fab, you'll find that people wear little rubber or little paper booties. They wear with ground straps on them. They have to wear face masks. They have hoods. I mean, they look like something out of an outer space movie, because these areas have to be perfectly clean. They have to be very clean. The water used has to be very clean. They refer to them as a clean room, right there. So they cut these into little pieces right there, and that's what we've got right here. That is the result of the manufacturing process there, that there. Right there. And then the wires that come from here go to various places on the silicon chip, and they're bonded to that there. Texas Instrument has a plant. My wife's nephew works there, right there at Carmine AU. It's right off. You'll see it if you go down the MRR2 toward Gambach. It's on the, as you head toward Gambach, it's on the right side. You'll see a plant that says Texas Instruments, and that's what they do there. They actually take the wafers and they cut them into dies and then place them into the IC. There was another company that did a lot of that called Chip Pack. I think they're out of business now. Out there, they've moved that elsewhere. So a lot of that work is done locally out there. But this is the process of making the IC. The actual IC, if you look at this piece of this right here, this is, for example, here's the actual IC right there. The IC is extremely small in comparison to the plastic packaging. And this packaging can be plastic, it can be ceramic, it can be glass. That's there. So, but this is what we're showing in terms of what's happening there. This is actually not part of this class, but I'm kind of going off. Since this picture's here, it's kind of good information to know, especially since a lot of this work is done locally. That's there. In the U.S., I don't spend nearly as much time on this because Fort Wayne, Indiana, we didn't make ICs there. We just bought them. That there. I mean, that there. Here, the chips are actually fabricated and packaged into the packaging, so it's a little bit more interesting. Some of you will probably find yourself working in companies that do this type of work right there. So, right there. And again, we get into this again. The chip itself is inside here, right there. They don't show it in the picture. This is an Altera part. Altera, I think, is still making their ICs in Penang. I think their fab is in Penang, out there, which is not far from here. Out there, I know that Atmel does a lot of their fabs in Malaysia. Who else is it? I'm thinking AMD does some of their fab work in Malaysia. So a lot of the IC manufacturing is done locally. Out there. So my experience has been how to use the IC, not in how to build the IC. Out there. So okay. Out there again. I'm not spend much time on this here right there. I'm just going through these slides because it's some material that's a little bit interesting. This is a typical TTL inverter. Here's an input right here. Here's an output right there. This is VCC. That's, again, they're showing here the pin numbers on the chip right there. Right there. And this is a resistor. A resistor is used by just simply running through some of the silicon material that's either positively or negatively charged. A capacitor, this is a PNP transistor. This is another PNP transistor. This is a diode. These are all made on that IC right there. This is a tiny, tiny speck of the IC is this actual circuit right there. So, and what we see here is a standard transistor circuit. I'm not going to go through this circuit. I don't know how much have you, where are you on your analog circuits course? This is a 100 level course, so you probably haven't had analog electronics, have you? Have you had Class A, Class B amplifiers? Right there. So okay. Right there. Some of you are saying, yeah, you've heard of them. Right there. I'm not going to go through this. This is a standard push-pull Class B amplifier is what that is right there. Now, the important thing to point out on digital electronics here, and I didn't get into it much in the first chapter, is that if you take a course in analog electronics, you're talking about amplifiers normally. You're talking about waveform shaping. You're talking about analog. Digital electronics have two states, on or off, right there. This is operated as a switch, right there. So the output of this is either going to be high or low, right there. High or low. This circuit happens to be an inverter. I'm not going to go through the logic to explain how it works, but if this input is low, this output's going to be high, right there. This is going to be low. So when we do that, yeah, I'm going to skip through this one here. This kind of goes through all the various right there. There, this is, again, notice that they're quad NOR gate, NOR. 7402 is quad NOR gates up there. This is the same type of circuit with using CMOS. And that's a particular, you have bipolar transistors, you have CMOS transistors, right there. Electronically, they're different. Right there. For the sake of this course, we're not getting into the difference very much. You know, the difference is the amount of power they use, the amount of time it takes for the outputs to change, the timing configurations, how much static, right there. Now, there are some differences that we need to talk about, is that we're dealing with TTL. If we have a floating input, it looks like a 1. If we have CMOS and we have an input that floats, it can cause it to overheat and burn up. So that there, some ICs have circuit protector. This is just kind of a rule that there, if you have unused pins, tie them to something. Don't let them float. That's all this slide is leading up to right there. Now this will show up on your final exam. It is showing up on this semester's final exam. You have to recognize these two tables. They're different. I concentrate on this one right here. This is just saying what the levels are. Anything between 2 volts and 5 volts is considered a high. Anything below 0.8 volts or 0.7 volts is considered a low, right there. Everything in between is up there. Those levels change when you go to CMOS because this goes to 0.5 and 1.5. Same basic thing up there. So stick this slide in your little memory bank up there. So, and I'm going to skip through the rest of this right here. We talked about this as using Quartus, and I'm going to skip through all this troubleshooting. Although, to be honest, troubleshooting is a skill that you will pick up later as you go through and things don't work right. But this is a engineering course and not a technician course, so therefore we don't teach as much troubleshooting. Okay, and I'm probably running a little bit out. Well, let me check my time right here. Yep, I got a few more minutes I could talk right there. I started late, that's why it seems like I'm running longer than that. Okay, programmable logic right there is basically, we kind of introduced that, PLDs. This is a good drawing of a switch matrix for a programmable logic array right there. We have 2 inputs, A and B. We have 2 inverters. This rail right there is B naught. This rail is B. This rail is A naught, A, right there. And then we can connect it up to these products right there. So we could connect, in other words, we put a connection here, 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 right there. We can connect those up there. Right there. So that's one example, and I kind of went through some of these the other day, right there. And right there. Okay. I was actually going to get into a little bit of VHDL today, but I'm going to right there not get into it. I will get into it right there. This is HDL. I have another set of slides I want to use for right there. Basically, all right, let me just go through this here, and then I'm going to call it a day here. This is a typical circuit here, and this is why I don't necessarily go too crazy about Karloff maps, because if you look at this particular file right here, this is an Altera file using VHDL, which is a common higher design language. And I've got a truth table right here. It's got a 1 here, a 1 here, a 1 here, 4 1s right there. Right there. And what I've got on the right is I've got a VHDL description for this particular circuit right here. This says that this is a figure 4. This is just the name of it right there. You know, we can name that whatever we want it to be named. It's got 3 inputs and 1 output right there. So the top part of this is called the entity. That just simply says that this is a black box with 3 inputs and 1 output right there, and what they're called. The second part of this is the architecture right there, and this tells me what's supposed to be inside the black box right there. And this is, we're going to call this the architecture, and this is the truth table right there for this particular circuit right there. We're going to say, we're going to form an internal signal that's a 3-bit vector. It's a 3-bit number, binary number, and a 3-bit binary number there. And then we're going to say that those numbers are, that 3-bit number is the same as our inputs A, B, and C right there. So we tie that internal. Then we have something here. This is concatenate the input bits into the bit vector. And then we have our next line right here is we say, this is the key thing right here. Right here. We say with this bit vector, select Y to be what for each combination. So if you look at this right here, 0, 0, 0, 0, 0, 1, this is my truth table, right? This is the same as this right here, just in a different format. So if I go through here and I see 0, 1, 1, 1, or 0, 1, 1, 0, 1, 1, I have a 1 for my output. So I go straight from my truth table straight into my VHDL code. I don't worry about AND gates, I don't worry about OR gates, I don't worry about Karnoff maps, I don't do any of that stuff. I just simply say, tell the software, design the circuit. And then the software designs the circuit. I've downloaded to the board like I did on Tuesday, and I can test it. So everything that we've learned up to this point, a lot of it we don't use anymore because we're relying on software to do the exact same thing. Now if we go back to a previous slide, this is the same thing in AHDL, that's a different language. Verilog is not covered in these slides, but Verilog is a third language. But you can see it's the same thing. We've got our subdesign here where we define what our black box looks like. Here's our table right there. Here's A, B, C, our inputs. Here's our truth table. And then this is Y, and this is what Y should be equal to. So we take the same truth table and we put it into the syntax of the language. Again, you know, this is actually my favorite language. I really like this for teaching, but it's obsolete. They don't support it anymore. Back when this book was written, it was supported, and it's in our version of Altera, but it's not used. Nobody in industry uses AHDL. Not there, but it's a good language for teaching because if you look at that syntax and you look at this syntax, you'll find that the syntax is a little easier on the first slide. But this is the syntax we have to live with right there. So from time to time, I'll be kind of introducing this, putting some parts of this language in there. And the key thing is that we can mix and match in our design right there. And I'm not going to get into this too much detail. Matter of fact, let me just stop at this point right here. We can mix and match between VHDL and schematic drawings. So some of our circuit can be schematic drawings, some of our circuits can be VHDL files. That's there.